angle coming from the cone. All right? It cannot come from the cone. So this is the angle about theta. If I pick any point within this cone, I line this point with the origin. So this ray can go as near as to z-axis to the cone, and as far as xy plane. Can you imagine that? No, not at all. So if this is the ray here, so this point is changing within the solid, then this ray is also changing. All right? So this changing, if my point is actually coming from the cone, I'm going to get a very small angle, which is exactly the angle formed by the cone. All right? You're convinced about that, right? Imagine if this point is right here. If this point is very near the origin, this point can be as large as pi half as the angle formed, right? So the largest angle we can form is actually coming from x-axis or y-axis. Any point you can have on the xy plane. In other words, to put it in the simplest word, this point is where the sphere is tangential to the xy plane. By tangential, we mean the angle is 90 degrees, right? So this is where it is tangent to xy plane. So it is tangent to the xy plane. That is exactly talking about the angle we can form is pi half degree. Okay. So my angle here is going to go from pi divided by 4 to pi divided by 2. It is pi divided by 4 because this angle formed by the cone is exactly pi divided by 4. Okay? Again, if you're not fully convinced why it is pi divided by 4, we have to put these two equations together. We have to put these two equations together. Because if I want to find what this angle is, I want to find what this angle is. This angle is exactly the angle formed by the intersection between the sphere and the cone. All right? So putting these two together, I'm writing rho is equal to 4 cosine phi, and phi is equal to pi divided by 4. And this will simply imply pi is equal to 4 divided by pi. I don't even need to care about the first equation at all. All right? Because the only equation I need is the angle formed by the cone. The cone is giving you the angle pi divided by 4. All right? So that's why I begin from pi divided by 4. The reason it is ending at pi divided by 2 because I need to look at the first equation of sphere. The sphere is tangent to xy plane, and that's where I see 90 degrees. Okay? That with me? So you have to convince yourself in this geometric setting here. Okay, so the angle is coming from pi divided by 4, coming from the angle of the cone, and pi divided by 2 coming from the angle formed by the sphere. Okay? And then I need to look at the longest distance and shortest distance in every ray going for 5 degrees. Okay? So if I look at the shortest distance for the points within this region, if I fix a ray of 5 degrees, okay, the shortest distance is going to be 0 going from the origin. But think of the longest distance you can form. The longest distance on this ray within the solid region has to be coming from the point on the sphere. All right? Yeah. If it is on the point of the sphere, then this distance has to be defined by the sphere equation. All right? Which is 4 cosine phi. Okay? So this will be the procedure to determine the intergradient ranges. Okay? Okay, so I want you to have this mental picture inside, especially in the very beginning. I taught you about how to understand rho, how to understand phi, and how to understand theta. So remember, rho is talking about distance. Varying the distance, it can go near the origin, further from the origin. If you vary phi, you're talking about the angle formed between the ray and the z-axis. So you can go from a positive direction of z to a negative direction of z. And theta is talking about the rotation around the axis. Okay? So in this particular case, theta can rotate for 2 pi. Phi can only go from pi divided by 4 to pi divided by 2. And rho can only go from 0 to a point on the sphere. Okay, so convince yourself what these 3 coordinates are trying to do here. Okay? And then, if I look at this triple integral, I have to be super careful. Because when I look at these intergradient ranges, this is number by that function here. So I cannot simply break that into 3 independent integrals anymore. Okay, so I have to be careful. So regardless of whether you have number or not, you can always evaluate step by step to eliminate the integrals one by one. Okay, so that is always working. Okay, so I don't break it into 3 independent integrals, but I can always evaluate them one by one. And also, as long as you identify this domain, the integrating domain, the following work is much easier. Comparing to identify the integrating region, the evaluation, the actual evaluation is much easier. Here, I'm trying to find the antiderivative for rho squared, all right? So my rho squared is still rho cubed divided by 3 sine phi evaluation from rho is equal to 0 to rho is equal to 5 d phi d theta. Okay, so it's going to be from 0 to 2 pi. So I have 5 and 0, so it's going to be.
Why is it from 0 to 5?
Which one? Theta?
No, isn't it supposed to be from 0 to 4 cosine 5?
Oh, sorry. Oh, I was trying to copy from here. Yeah. That's a huge mistake. Yeah, sorry. This is going to be 4 cosine 5. Yeah, thank you. 4 cosine 5. So that's why I'm getting 64 divided by 3 cosine square phi sine phi. When rho is equal to 0, I don't get anything. So it's from pi divided by 4, pi divided by 2, d rho d theta. Okay? Yep, I think I'm doing the correct computation here. Now, in fact, I can break this into 2 independent intervals because both these two are numbers. But this is not very crucial here, right? Because the integrating function has nothing to do with theta. In the end, it's just a matter of multiplying by 2 pi. Okay? So this is going to be from 0 to 2 pi. So I can bring out the constant here. So it's cosine cube phi, sine phi, d phi. The antiderivative function is going to be cosine to 4, right? Cosine to 4. Then when I take the derivative, I'm bringing down 4 in cosine cubed. But then I need to multiply by minus sine phi. All right? So in the end, I need a minus 1 over 4. Evaluating from phi is equal to pi divided by 4, and pi is equal to pi divided by 2. Okay? d theta. Again, if you're not very sure about this antiderivative function, you can take the derivative. You gotta get cosine cube phi multiplied by 4, so it's gonna cancel the 4, and then multiply by minus sine phi. That's where I'm getting a sine phi right here. All right? Yes? Okay, so these steps you can check afterwards. So key thing is how to identify the region. These things you can all do afterwards. So when I plug in phi equals pi half, cosine pi equals 0, so this is going to be disappearing. And when phi is equal to pi divided by 4, I'm getting square root of 2 divided by 2. So it's going to be 64 divided by 3 multiplied by 2 pi coming from theta integral, and multiplied by 4 square root of 2 divided by 2, then to 4th power. So in the end, it's going to give me, so it's 1/2 then to 4, so it's going to be 1 over 16, and 1 over 64 is going to cancel this, no? No, it's going to be 1 over 2 to 4th power. It's 1 over 2 multiplied by 1 over 2, so it's going to be 1 over 4, right? So it's 1 over 16, so I got a 4 and 2, so it's going to be 8 pi divided by 2.
What about the 3?
Oh, 8 pi divided by 3. All right? 8 pi divided by 3. So this is still a pretty straightforward computation. So within 100, so I would say it's a moderate computation. Okay, questions? Questions? I want questions for particularly how to identify this region. Okay, how to identify this? Yep.
I'm still kind of like not clear about like how you got the limit of integration from pi over 4 to pi half. Like, I don't see like.
So the seed identification is probably the most challenging part. All right. So now imagine you're the point, you're a point flowing in this solid region. Right. So every time I have a point, I can line this point with the origin. So basically, I want to see if this point is changing within the solid region. What is the smallest angle I can form with positive direction of the axis? All right? That is going to be the lower bound right here. The largest angle I can form for this ray with positive direction of the axis is going to be the upper bound. Are you convinced? So I'm saying if this point is changing within the solid outside of the cone, the smallest angle is going to come from the cone. So this point is exactly on the boundary of the cone. That is where I can achieve the smallest angle right here. That angle is given by the cone, which is exactly pi divided by 4. All right? Are you convinced? That's the smallest angle. At least a little bit more convinced, right? That's pointing to the same direction. And then I'm saying the largest angle I can form is where I'm tangent to xy plane. If I'm tangent to xy plane, that angle is exactly given by xy plane. So any point on xy plane, you line a ray and form a pi divided by 2 angle with the positive direction of x-axis. All right? Because the z-axis is orthogonal to xy plane. This sphere is tangent to xy plane. That's why when I have a point which is very, very close to xy plane, that's where I achieve the largest angle. Right? So imagine if your point is going near and near the origin, it's going to go near and near xy plane. So the angle is going to go near and near pi half. That's where I have the upper bound of pi half. Okay? So try to convince yourself by your own words, no matter how you convince yourself. You can draw the picture, or you can even use computer to draw the picture and see how this angle can vary. Okay? Yep.
For the largest ray, it should be on the function of that cone as well.
Well, not really, because the cone is open upwards. The radius can go to infinity, right? So if I'm looking at the point within the solid region, the longest distance I can go is actually on a sphere rather than on the cone. All right? If you're on the cone, your radius can go from 0 to the infinity, whereas this is a bounded sphere. So if this is within the sphere, right? This is the condition. It has to be inside of the sphere. If it is inside of the sphere, the longest distance you can go from the origin is the point on the sphere. And the point on the sphere, the distance, the radius, is exactly given by 4 cosine phi. Okay? A better news here is this is going to be the most challenging question in spherical coordinate system. Okay? So as long as you can crack down this problem, you should be pretty okay. Okay? So unfortunately, I don't really have too much time to convince every single one of you. But if you wanna discuss with me afterwards, I'll be very happy to talk you into this. Or a better way to do this is you can convince your colleagues, and you can talk to each other and see whether you can convince each other. So next, I want to discuss coordinate 27. Change of the variable. Okay. Change of variables is much easier than spherical coordinate system. So this is even. Okay. So our second midterm is going to cover everything in chapter 14, except section 14.6. Okay. So this is still within the range of our test. So I want to. Okay. So you can talk about the spherical coordinate system afterwards. Okay. So let's fix our change of variable now. Okay. So a quick switch of mindset. This is much easier than spherical coordinate system. So I hope you guys are happier here. So we have done change of variables all the time. Right? So sometimes we don't even realize we're doing change of variables. But I want to mention the formula So if I'm taking the integral, okay, now this seems our best friend forever. So single variable calculus. Single variable calculus, I can change the variable from x to u. If x is equal to g of u, then I can write this as f of g of u. I also have to change dx to g prime u of du. Right? So these are all straightforward. You switch between x and u in a function, you change dx to g prime du. But one thing is pretty important here is you have to worry about the initial and the terminal point. All right? You have to change from the range with respect to x to range with respect to u. So usually it is g minus of a and g minus of b. So you're taking the pre-image of a and b. But in particular examples, even though we're using this formula, but a lot of cases you don't realize you're using this formula because you're simply changing the variables by the formula, and then you see what the numbers are changing from one pair to the other pair. Right? So usually you're using this without even knowing you're using this formula. So I want to generalize this change of variable formula into 2 and 3 variables. I want to do this in double integral and in triple integral. And I want to also mention we have already done this in several different occasions. So one occasion is I begin from XY coordinate system and I change it into a polar system. All right? I change it into a polar system. In polar system, the intervening region will be different. And I have to change between x and r and theta. So I have to change x to r cosine theta, y to r sine theta. And then I have to also have dA, which is the integrating element with respect to r and theta. But if you compare what happens in the single variable case, you have this one extra factor of the derivative of the changing function. All right? This is the additional factor when you change the variables. So in the double integrals, when we change it from xy to r and theta, we have this